Alright, let's have a look at Coulomb's law. Let's say we have two charged objects that have a charge Q1 and Q2 on them, and we place them at a certain distance apart. Now what Coulomb found was that there was an electrostatic either repulsion or attraction between those two charges, depending on whether there were two negative charges, two positive charges, or one of each. And what he found was that this electrostatic force of attraction or repulsion was dependent on the size of each of those charges. So in other words, if we increase Q1 by a factor of 2, the electrostatic repulsion would also be increased by a factor of 2 as well. And similarly, if we increased Q2 by a factor of 2, the same thing was found. So what he said was that this electrostatic force is proportional to the product of Q1 and Q2. He also found that it was dependent on the distance between these two charges as well. So in his experiments, he found that this electrostatic force was dependent on the inverse square of the distance. So in other words, as this distance increased by a factor of 2, the electrostatic force decreased by a factor of 4. And he finally formulated his equation. So there was some constant in there, but the electrostatic force was equal to Q1 times Q2 from this relationship over d squared, where this value k is a constant and it's equal to 1 over 4 pi, and this is an E0, which is the permittivity constant. So k, in our case here, is equal to 9 times 10 to the 9th Newton meter squared per Coulomb squared. Now this equation is very similar to our force of gravity equation. We've got a constant, g for our gravity, k for our electrostatic force. We've got M1, or the product of M1 and M2, the product of Q1 and Q2, and they're both over d squared. So we've got some similarities between the two equations. They're both forces that act over a distance rather than by contact, but we find that force of gravity acts over a much greater distance with much larger masses. On the other hand, our electrostatic force operates over very small distances, but typically with smaller charges as well. So let's have a look at this one in action. And to do that, we're going to take a simple question. Let's have a look at determining the electrostatic force exerted on one electron by the nucleus of a hydrogen atom. And for this, we're going to take the average distance between the nucleus and the electron to be 0.53 by 10 to the minus 10 meters. So I've done this two ways. On the left-hand side, first of all, we're going to get the absolute value for this electrostatic force, and that's equal to kq1 q2 over d squared. If we put our numbers in, our k value is 9 by 10 to the 9 Newton meter squared per Coulomb squared. Our charge on an individual electron will be 1.6 by 10 to the minus 19. You'll notice I haven't put a negative sign in there because we're looking at the absolute value. Similarly, the charge on one proton, because that's what's going to attract that electron, and there's only one proton in a hydrogen atom. We've got 1.6 by 10 to the minus 19 coulombs, and that's going to be over the radius of our the distance between our nucleus and electron all squared. And this gives us a value of 8.2 by 10 to the minus 8 newtons toward the nucleus. So remember, the electron is moving toward the nucleus. We go from negative to positive. Now the other way that we can do this, before we move on, the other thing about this is we calculate this absolute value and then we determine direction afterwards. So that's one way of doing it, and that method will come in handy when we do some of the more complex questions. But we can also look at it in terms of our positive and negative charges here. So we've done exactly the same thing here, but we've put our positive charge on our proton, our negative charge on our electron, which once we go through exactly the same calculation, we get this value of minus 8.2 by 10 to the minus 8 newtons. Same scalar value, but the negative in this case denotes that we have a force of attraction between the proton and the electron. Now, as I said, we can use this where we get positive and negative. When we get to some of the more complex problems, we'll actually start using this method over on the left-hand side.